Hi, good morning. We're gonna look at today SN2 reactions mechanism. So under the big umbrella of nucleophilic substitutions, we have two mechanisms to be discussed. That's first we're going to discuss SN2 because it makes more sense to learn it first, and then we will be talking about SN1. And so we already had the word cloud. We are a bit familiar with what these terms are. So the nucleophiles are Lewis bases. They can donate a pair of electrons to make a bond, specifically to the carbon. And so we're going to be ranking them, their strength, nucleophilicity, and also what's the trends in the periodic table, and also what are the strong, what are the weak nucleophiles. And then we also going to look at the substrate, that's the carbon atom, which will become an electrophile, delta plus, partial charge on it, because it's attached to a electronegative atom or a group which is a leaving group, right? So these terms we're going to be using quite often. Now we're going to be looking at SN1 reactions are not stereospecific, and we're going to look at that, and then also how to use a decision tree in order to use to find out, predict what mechanism should be applied to that, right? And then of course this portion for the people from the biological streams, and there are important few reactions that we can talk about, and then the lab. Now here, yeah, just to notice that why the stereospecific reactions are important. If you look at think about the DNA methylation, so specific coenzymes, enzymes, and then it's specifically methylated cytosine. It's one example, and another one, actually look at this one. So here is a asymmetric center. This is the other one, the object and the image, and look at the one is a sleep inducing, the other one is a teratogenic. So there should be a really important thing in biochemical reactions, right? So let's look at today the big picture. So nucleophilic substitutions. So you can simply think it's the substitution nucleophily mechanisms depend on the strength of the nucleophile, the stability of the electrophile, and also the quality and the ability of the leaving group. So the carbocation intermediates can show migration, and also it depends on their structure, and this is only on the SN1 mechanism though. Transition state is also a proposed mechanism. Then we won't be able to see anything in a laboratory, right? So the SN2 mechanism, this is one of the most important reactions in organic chemistry, the very common one. And resources and activities for you folks, we will do the starting with the word cloud and looking at what's the learning goals, right? And then we're gonna be doing, after the recorded lecture, listening at your own pace, and we're going to be looking at the class version of summary. We will work together and we will solve problems based on that, right? And then also we will be making this diagnostic tool for substitution, addition, and elimination. That's all together from the previous lectures and the next few classes. And substitution reaction mechanism and animation, so I will put some hyperlinks there too, right? Now here, so the SN2 concerted mechanism. So what's the concerted term? The one step. Look at this on one arrow, it's one step, and it's also concerted, it's happening at once. What's happening at once? Let's look at here. First the leaving group, look at that one, leaving group, that's the chloride. Electronegativity creates here delta plus here on the carbon, and delta negative in the chlorine atom. So therefore it's preferred to take these 2 electrons to chlorine atom, right? And then now, like, who's going to support that one? Look at the nucleophile. negative here, lone pair here will attack the electrophilic carbon because this is delta positive partial charge, this is a negative, so there is a possibility of attacking. So this is the simultaneous work, breaking bonds and the forming bonds, and that will give you one step product here, and then the leaving group is here. It's quite stable because of the complete shell on the chlorine, or relatively stable Cl minus, right? Now, yes, so also it's a good thing to notice, if I want to get more products here, I need to increase this and also that, right? So therefore it should be, the rate should be depending on the concentration of these two. So that's why we can call bimolecular. And here, so the attack from the back, so that's what I want to highlight here. See here, if the nucleophile is trying to come this way, and this is a bromine atom, much larger, a lot of electron cloud, and this is a negative ion, so that's much larger electron cloud, so these should not be reaching this direction, and it's blocking straight, right? So therefore what's the possibility is going from here, so that's why leaving group here, attack comes from here, that's why it's called the backside attack or back attack, right? So that happens here, and then it kicks out, and it's a simultaneous concerted reaction, right? So it's a good way to think. Look at the incoming group, and here the nitrile, right? So look at the gusty wind, the umbrella, what happens to the umbrella? It flips, and that's similar situation for this little umbrella. If you can figure out here, that's a little umbrella, we use it for configuration of RNS, and here's the umbrella flipped the other way around, right? So it's going like that. So, and now we can move to so the inversion also happens, next one. So you can see here, I notice S and R. So if you remember your CIP rules, we can just take a look at one of them whether it's true. So this is the priority 1, priority 2, and priority 3. 1, 2, 3, that looks clockwise, but the hydrogen is in the coming towards me, so therefore we have to flip the sign, that should be S. So similarly you can try that one too, right? Yes, so inversion, so a bit more details about the inversion here. So this is another example. So first thing, I kind of like to see whether you can do this classification, identifying each component, right? So the leaving group, the electrophile, the nucleophile, the transition state, leaving group again, and the product. So it's good to kind of identify which one is which. And now we go on to this one here. So the nucleophile attacks, and the chlorine atom moves out, right? And we can see we have given hydrogen, deuterium, tritium, and so it's the S configuration. Then after the transition state, and then what happens is the OH is actually attached from the other side, so it should be Walden inversion happening here, the inverted absolute configuration from reactant to the product. So that's what we are looking at here. Now, yes, again, attack from the backside and simultaneous, and few more details now we can look at. We know the details already, right? And transition state is making bonds and breaking bonds. It happens at once, and you put it in the parentheses and with the double dagger sign, and that's one reaction. Actually this should be one arrow, and that's what the reaction is, right? Let's see what else we can take home from here. And the transition state is hypothetical, and it's not like an intermediate that we can isolate and see that like a carbocation. And transition state is here, and it's high energy, and it's hypothetical, theoretical. And then look at the reactant here, product here. So the free energy can be indicated here with the reaction progress, right? Okay, now we're going to be going to the SN1 next, so we just stop this one here and we move on to the writing pad. Yes, so we're going to look at let me draw on the screen here. So if I start a reaction, let's say without knowing, I'm just trying to understand what's this reaction, right? If I am trying to understand this reaction, let's say you have this one, and then I'm gonna put a solid wedge and a dash wedge, and this is the solid wedge. Let's say this is Br, this is hydrogen, so I put it that way so easy for us to figure out whether it's R or S, right? And then this will be reacting with sodium cyanide, right? And then if it goes to the reaction, let's see what happens. So I want to identify a couple of things. So solving or working on this type of problems, I want to see sodium, lithium, potassium, and we will add a positive here, and then that's not reactive, and negative on the CN carbon. So that's the nucleophile. Let's identify nucleophile, and then here the leaving group. Let me put that here. So here is the Lg, and this is delta minus, and this carbon should be delta plus here, and this should be E plus. Then let's identify that, and then we neglect the sodium, potassium, lithium, and then the Cn minus is the nucleophile, right? Now if I try to attack from this, let's say, let's take this one here. If I try to attack from here, it will not go, because bromine is negative, Cn is negative, at their bulk here, larger, they will not be supported. So what happens here, now we can see there is a gap this side, right? So that means this can come from here to there. So that we should call it then back attack, backside attack, right? So that's what should be happening. Now if that's happening, so we can write here transition state, and I'll put a double dagger sign, and it's one arrow for the one step, and we can draw what we are doing here. So NC, and connecting to the carbon here, and Br is leaving, so bond breaking happens here, bond forming happens here, right? Bond breaking and bond forming. Now the rest we're going to just leave it as it is, right? So the hydrogen would be here, and then I want to put this, right? And that's the transition state. Let me put here transition state, and it's a pentavalent, 5 points touching, and it's theoretical. And let's see what happens, the result. So bromine already, now we can mark it here also. So the bromine leaves, simultaneously Cn comes in, right? So therefore I'm just going to put the bromine here, negative octet complete cell, and it's pretty happy it's going to be there. Now here what happens, so I can put the, and because Cn came from the bottom, so I need to put Cn here, and then hydrogen is the little guy, it will be pushed like that. So now from that we can just quickly get the RNS configuration for this one, So we can see this is the fourth group, this is the first, this is the second, this is the third, 1 2 3, and the hydrogen in the background. So 1 2 3, it is an S configuration, and here you have 1 2 and 3, right? 1 2 3, and it seems S configuration, but hydrogen in the foreground, so there should be R. So that's the inverted product, or inversion happens. That's an important piece. So I would say the labeling 1, the reaction 2, the stereochemistry 3, right? So we're going to look at a few other things here quickly. And if I want to get more products here, so what I need to do is I need to increase the rate, and the rate will be increased in this fashion. So number 4, rate will be directly proportional how much of the electrophile and how much of this nucleophile I have. So I can increase those two to get the product. So the proportionality is not a good thing that we have to give a value. So we go to the rate is k to the that's the equilibrium constant, right? So that's a rate constant actually. So the proportionality constant, we put it there, so E plus and Nu minus. So that gives me the bimolecular, right? Now, so another thing I want to look at, so that's done actually. Number 5, I want to look at the energy. Now, if I look at the energy, so that would be here. In this case, it's one step and concerted reaction, so I should be having a reactant and the product, and that's the progress, and that's the energy, and I would be having something like that. The transition state is here, right? Now we can put them together, right? So look at that one. So now I can say it what we have done so far. We can put here the Br is substituted by Cn, so it is a substitution nucleophile, and this bimolecular should be there. So we should name this one with a lot of details, SN2, right? Okay, now we can do similarly the SN1.